Welcome, ladies and gentlemen, to the 7th episode of CS341 Algorithms, where today we're going to be jumping into the topic of greedy algorithms, the greedy algorithm design paradigm. So what is a greedy algorithm? Well, before I get to greedy algorithms, I want to talk to you about the types of problems that we typically solve using greedy algorithms. So we usually use greedy algorithms to solve optimization problems. That's not to say that optimization problems are usually solved by greedy algorithms. Optimization problems are solved by all sorts of algorithms: divide and conquer, greedy, dynamic programming, things like linear programming. But greedy algorithms are usually used to solve optimization problems. Okay, so let me run through a few definitions here. So what's a problem? Well, given a problem instance, which of course is just an input for that problem, find a feasible solution. We'll talk about what feasible means, that maximizes or minimizes as appropriate a certain objective function. Okay, so this is a pretty jargon-filled sentence. This is what an optimization problem is. And let's go through all the jargon. So we know what a problem instance is. Let's describe what problem constraints are with a little example here. So suppose we have some two-dimensional problem that we're trying to solve. We're trying to optimize some function of two variables, x1 and x2, and we can draw these two variables. We can draw, axes for these two variables, the x1 axis on the bottom and the x2 axis going up vertically. And constraints, in this case, this is a linear program. Constraints represent some sort of requirements that have to be satisfied by any feasible solution. So for this linear program, the constraints are x1 plus 2x2 has to be less than or equal to 8. 3x1 plus 2x2 has to be less than or equal to 12, and so on. Each of these constraints actually represents a line, right? There is a line where x1 plus 3x2 equals 3. That's this line down here. And the inequality doesn't represent a line, but rather a half plane. So basically, you can think in a linear program, linear meaning you have a linear combination of variables and the constraints are linear constraints, inequalities on those variables. In a linear program, you can think of these constraints as creating half spaces and the intersection of all those half spaces. So for example, x1 plus 3x2 greater than or equal to 3 is the half space to the north up from this line, x1 plus 3x2 equals 3. And then you have this line, 3x1 plus 2x2 equals 12. If this inequality says we should be less than or equal to 12, then this constraint represents the half plane to the left of this line, this diagonal line here. And the intersection of all of the half spaces defined by the inequalities creates this region that's highlighted here in yellow, and we call that the feasible region, because that region consists entirely and precisely of the points that satisfy all of the constraints. So for any problem instance I, feasible of I, which is this yellow region, is the set of all outputs, i.e. solutions, for the instance I that satisfy the given constraints. Okay, so that's what a problem instance, constraints, and feasible solution are, but we don't just want a feasible solution. We're talking about optimization problems, so we want to select somehow the best solution out of all these points. And we want to select, define what better means so we can select the best by using some sort of objective function. And so you can think of the objective function as a function f that maps points in the feasible set into the feasible set of solutions, or the set of feasible solutions, into real numbers, non-negative real numbers. And you can think of this objective function in some cases as being a profit function if we want to maximize it. You can think of it in other cases as being a cost function that we want to minimize. Okay, so that's what an objective function is. Now we can define an optimal solution. So a feasible solution, x, is optimal if the profit of x is maximized, if x is the point such that profit is maximized at that point, or the cost f of x is minimized at that point x. And you can only consider the x that are feasible because we can't say that some output is an optimal solution if it gives a really great value for our objective function, but it's not even feasible. It doesn't satisfy the constraints. So in order for something to be a solution to an optimization problem, it has to be both feasible and optimal. Okay, so here's a couple arrows and a couple points that just express the things that I just described in terms of this problem. So for example, this yellow arrow is indicating that this represents the set of feasible solutions. Each of these feasible solutions has an f value. So for example, this point here might have an f value of $720 of profit and an f value here of $907 of profit, and this would be better according to that objective function. This solution would be better according to the objective function f. Okay, so how do we solve optimization problems? Well, there are tons of techniques. In this course, we're going to study greedy approaches first. Well, technically, we've also studied divide and conquer approaches already, and you can indeed solve some optimization problems using divide and conquer algorithms. We're going to study greedy approaches now, and then a little bit later, we'll study dynamic programming, which is sort of like divide and conquer, but sometimes it can be a lot more efficient than divide and conquer, especially if the subproblems that you're solving have some sort of overlap. And we'll talk more about that when we actually get into dynamic programming. But what's a greedy algorithm? Well, greedy algorithms are usually very fast, and the algorithms are very simple, but they're hard to prove optimality for. So usually the challenge in a greedy algorithm, there's a little spark of creativity you need, and then you need to put almost all of your work into the proof. And that's basically what we're looking for you to prove rigorously that your results are optimal, because the algorithm usually has kind of almost nothing to it apart from the work that you need to do in the proof. Okay, so greedy algorithms follow a particular structure, it can be kind of hard to define. And the definition of what makes an algorithm greedy, there are very rigorous, precise definitions, but they're not the kind of thing you want to go through in a third-year algorithms course in an undergrad degree. These are things you might want to go through in a 6th or 7th or 8th year grad course. But nevertheless, I'm going to do my best to give you a definition that's not completely formal, but gets at some of the intuition that underlies the real formal definitions of greedy algorithms, that you can find elsewhere in more advanced courses. So roughly speaking, a greedy algorithm starts from nothing and then makes a sequence of irrevocable choices one at a time, and these choices aren't based off of global knowledge of what will be optimal many choices in the future. They're sort of nearsighted choices that are based off of doing something that seems like the best move right now if I'm not looking far into the future. So there are a couple of concepts that are going to be helpful in describing how greedy algorithms work. So let me define for you partial solutions and a choice set. So for partial solutions, given a problem instance I, it should be possible to write a feasible solution as a tuple. So the feasible solution, capital X, is going to be this tuple, little x1, little x2, all the way up to little xn for some integer n. And intuitively, these are going to represent the choices that the greedy algorithm made. Each of x1, x2, and so on, each of those is a choice. Each of these xi's is in this chi, capital Chi, which is called the choice, the global choice set. This is the set of all possible choices you could take in an algorithm. So these are choices in a tuple, a sequence of choices. A tuple where I is from x1 up to xi, where I is less than n, so up to n would be a full solution, a feasible solution. If it goes up to something less than n, just up to xi, then it's a partial solution only if no constraints are violated. Can't violate any of those problem constraints. Otherwise, it's not a partial solution. It's not any kind of solution if you violate any constraints. So if you don't have a full feasible solution, you might, as long as you've satisfied the constraints, have a partial solution with only I of the choices made so far. And it might be the case that a partial solution you've developed so far can't be extended to a feasible solution. It might be the case that the first I choices you've locked in prevent you from making choices that will end in a feasible solution. So maybe you haven't violated any constraints yet, but maybe the first I choices that you've made have locked you into needing to make a choice in the future that violates constraints. Then you wouldn't be able to extend a partial solution into a feasible solution. But we would like to be able to talk about partial solutions that can be extended into feasible solutions, because that's going to be the rough structure of a greedy algorithm. We're going to build partial solutions into bigger partial solutions, eventually into a full feasible solution, and then make a sophisticated argument that it's not only feasible but optimal. So we'll talk more about that. Okay, now I want to define a choice set which is different from this chi. This chi is all possible choices that you could make, with no respect for whether that choice makes any sense at this moment. So this includes choices that would violate constraints. We want a way to talk about choices that don't violate constraints. So for a partial solution, x1 up to xi, we can define the choice set, choice of x. So x is the partial solution. Choice of x is going to be the subset of chi, where if I take one of these choices in the subset, I won't violate any of the constraints. So this is the set of choices that I can make starting from my partial solution x that will preserve my constraints and result in a new partial solution that consists of x1 up to xi, and now also the choice y. So really crucially, chi is the set of all possible choices, completely irrespective of whether they would violate constraints. And choice of x is just the choices I could make starting from my partial solution x that won't violate any constraints and will leave me with a new partial solution. And it could be that choice of x is empty. I might not be able to extend the current partial solution at all. Okay, so we've defined partial solutions and choice sets starting from a partial solution x. Now we need a way to make choices that actually allows us to come up with not just a feasible solution, but also an optimal solution. Because at any point in time, there might be a bunch of different choices that we could make. Our choice set could have 100 different options, and we want some way to choose one of them. If I just use arbitrarily, I'm very unlikely to come up with an optimal algorithm, so I need some sort of way to evaluate my choices to figure out which one is best. And I want my evaluation criteria to be local. I don't want them to depend on complicated calculations that predict many choices in the future to find an optimal choice. I want to just look at the set of choices I can make right now and the set of choices I've already made in the past. And without considering any future choices, just the single choice I can make now and the choices I've made in the past, I want to make the choice that seems best using only that local information, not the global future information about future choices, just local information about this single choice that I'm going to make right now, ignoring the future. So I need some local evaluation criterion function, g. So this is an evaluation function that's going to tell me, given a choice, y, and we might as well define it for all the possible choices, not just the choices that leave us with feasible extensions of our partial solutions. We can define it in terms of chi, and we'll only ever really evaluate the local evaluation criterion on the choices that we could actually make and leave us with a feasible solution. So given a possible choice, g of y, the evaluation of y, is going to give us some sort of measure of the added profit or the added cost that the choice of y, the local choice of y, ignoring future choices, would add to our solution. So how much would making choice y right now, where we are right now, impact the cost or profit that we're going to end up with? Now we're not going to think about future decisions. Okay, so what's an extension? Well, given a partial solution, x, x1 up to xi, we can choose some y in the choice set of choices that don't violate our constraints. And we choose that so that g of y is optimal over all of our possible choices that we could make in this step that won't violate any constraints. We want to choose the one that either minimizes our cost function, our local cost function g, or maximizes our local profit evaluation function, g. And then we're going to update our partial solution x into an extended partial solution, a new partial solution that's an extension of the old one, x1 up to xi, followed by our new choice, y. And this, with all of these things defined, has a lot of definitions. With all these things defined, now I can tell you what the structure of a greedy algorithm is going to be. We start with the empty partial solution, no choices made yet. We repeatedly extend our current partial solution with a new partial solution, bigger and bigger partial solutions, each of them an extension of the previous, until a feasible solution x has been constructed. Now, this feasible solution may or may not be optimal. Our job is to prove that our local evaluation criterion is configured in exactly the right way so that the feasible solution we end up with is also optimal. Okay. So here's some stuff I said, just written on the slides for your notes. Here's something I should point out. When we're deciding what our choice is for a given step, for a given extension, when we're going to extend, we figure out which choice gives us the best value of g of y, over all the different y's we could choose. And then we pick that choice, and that choice is irrevocable. We're never going to undo that choice. If we choose to include y, our final solution will be an extension of this. So y is irrevocably chosen, and that's crucial. That's a crucial part of this being a local, greedy method. We don't do complicated reasoning where we undo previous choices or look ahead and consider future choices. So neither do we look ahead and consider future choices, nor do we look back and reconsider and undo our old choices. So we're just going to choose the next element to include by greedily taking the y that gives us the maximum local improvement, whether that's maximum profit or minimum cost. Okay, so that's the structure of a greedy algorithm. And there are not necessarily greedy algorithms for all problems. There are lots of problems where we don't know good greedy algorithms for them, and it really doesn't seem like a greedy approach will work. So let's run through quickly, before we start seeing concrete examples of greedy algorithms, let's run through a couple of core characteristics of them. So first, as I mentioned, greedy algorithms do no looking ahead to future choices and no backtracking of previous choices. So you can't consider how your current choice affects future choices. You can't undo or change your old choices. Greedy algorithms can usually be implemented really efficiently. How? Typically, they consist of a pre-processing step, which is usually a sort, based on the function g. So usually g defines like a comparator for your sort, and the pre-processing step is a sort. And then that's followed by a single linear pass through the data. So you usually end up with an n log n time algorithm if you use an n log n sort. And if you're lucky and you have like, bounded integer inputs, then you could use a super fast linear time non-comparison based sorting algorithm like a radix sort or something. And you might even get a linear time algorithm. In a greedy algorithm, only one feasible solution is constructed. We don't explore multiple different paths to coming up with solutions. There's just a single path we take through the graph of all possible solutions, and that single path is dictated by our heuristic local evaluation criteria function g. And for correctness, for greedy algorithms, it's possible to prove that they always yield optimal solutions, but these proofs can be tricky and complicated, and that's where most of the challenge is going to lie. And we will see examples of these things, and you will be asked to do such proofs as well. Okay, so the first problem we're going to talk about that we're going to show a greedy solution for is called the interval selection problem. Okay. So what's the input to the interval selection problem? Well, there's a set A of time intervals. These intervals are labeled A1 up to AN, and each interval AI has a start time SI and a finish time FI. And of course, the FI is greater than or equal to the start time, and SI and FI are positive integers. And a feasible solution we have to define for this problem. This is basically defining what our constraints are. So this is part of the problem specification that's given to you. A feasible solution is a subset X of the input intervals. So we want to output some of the intervals. And those intervals have to be pairwise disjoint. You can't have any overlapping intervals, any intervals that overlap in time. So if you wanted to think about this problem intuitively, you could think about this is a kind of scheduling problem where, for example, you're scheduling a meeting room. And there's a single meeting room, and the time intervals here represent meetings. And you can't schedule two meetings to run at the same time. In fact, none of the meetings should overlap with each other, because then you'd be running meetings in the same room at the same time. So that's why they have to be pairwise disjoint. That's one way of thinking about this problem. So the output that we're looking for is a feasible solution, of course, because they have to be feasible. And what's the optimality part? Well, we want it to have the maximum size. Well, what's the size of the output? It's the number of intervals, the output, so the cardinality of our subset X of the input. We want to output as many intervals as possible that are pairwise disjoint. So here's an example input drawn, and I'm drawing these intervals where you can imagine time going from left to right. So the left endpoint's the start time, the right endpoint is the finish time. And I've drawn them on two lines here because, of course, when these things overlap, I can't draw them on top of each other without it looking very confusing. So I've drawn them, one over the other instead of, I don't know, drawing them in some other weird way. So, for example, we could take this interval and decide, yeah, this is going to be in our subset X that we're going to output. And we could reject this one and say that's not going to be in our subset X. We could take this one and reject these three. Yeah, okay. And we could just output these two, basically. And maybe we didn't even consider this interval, our solution, some weird solution that just looks at a subset of the input and decides to take a few of them and rejects the others, and some of them aren't even considered. Okay, you could write an algorithm like that, and it would produce some kind of output, but is it correct? Well, first of all, is this feasible? The chosen intervals don't overlap. So this really weird execution I just described, this really weird example, where my output's going to be just these two intervals. I didn't even consider this interval with my algorithm. That will be an algorithm that, well, at least in this case, produces a feasible solution. For this input, that algorithm produces a feasible solution. But is this solution optimal? Well, no. I mean, clearly we could take this box and we could get at least 3, so certainly 2 is not an optimal number. So there are a few different greedy strategies that we could follow to solve this problem. Let's explore a couple of them briefly. So here's a first possible strategy. We could sort the intervals in increasing order of starting times. In other words, in each step, we could choose the earliest starting interval that's disjoint from all the previously chosen intervals. Okay? So let me just tell you how this informal description of a greedy strategy maps onto the formalism I described a few slides ago. And I'm not describing this because you need to use this formalism. I'm describing this just so you understand the mapping, and then for most of this course, we'll talk about greedy algorithms in these relatively informal terms like I've described here in this box. But we should do so understanding how this maps to the theoretical concepts and objects I described above. So what is a partial solution for this problem? Well, it is an x equal to x1 up to xi, where each xi is an interval that we chose to output. That's a partial solution. This is only a partial solution if it's feasible. So in particular, all of these x1 up to xi must be pairwise disjoint. And indeed, we will produce, as we go in this algorithm, partial solutions that are feasible as we go, because we're always going to pick the earliest starting interval that is disjoint from all previously chosen intervals. So it's easy to argue that our x, partial solution x at all times in the algorithm will be feasible, and thus it will be a partial solution. It won't just be a subset of the input, it'll be a partial solution. Okay, what are our choices? Well, chi, the set of all possible choices, is just A. It's the set of all intervals. However, the choice set starting from a partial solution x is the subset of chi, in other words, the subset of A, such that the partial solution x, i.e. x1 up to xi, followed by y, extended to add choice y, still respects all the constraints. So this is the set of all choices we could make starting from the partial solution x. In other words, the set of all intervals we could choose starting from partial solution x, such that that interval y, when our partial solution is extended with that interval y, we still respect all the constraints. In other words, y doesn't intersect any of the previously chosen intervals x1 up to xi, right? So that's what the choice set is. It's the y in A where x1 up to xi as well as y it pairs pairwise disjoint. And what's the local evaluation function? Well, g of y is just the start time of j. We're always picking the earliest start time, so we want to minimize the start time of j. That's our local evaluation function. So our g of y is sj, where y is the jth interval. Okay, so g of the jth interval is the start time of that interval. Okay, so that's our local evaluation function. And you notice we're going to sort the intervals in increasing orders of start time. So we never actually need to evaluate this local evaluation function. It's going to be encoded in the sorted order, because at all times, the interval that minimizes this local evaluation function will be the earliest interval in the sort order that, of course, is disjoint from all the previously chosen intervals. That'll be the one that we pick. Okay, so let's draw out what this looks like. Sorry, we'll talk about that a bit more in a moment. Let's talk about the other greedy strategies, some other greedy strategies that we could try. So here's a second one. What if instead of sorting by start times, we sorted the intervals in increasing order of duration? So we, instead of starting with the earliest interval that's disjoint from all previously chosen intervals, we start with the shortest interval that's disjoint from all previously chosen intervals. In other words, the local evaluation criterion function here is f, the finish time of I minus the start time of I, the duration of interval I, whereas previously it was the start time of I. Earliest start, smallest, so smallest start, smallest duration. Here's a third possible approach. We could sort intervals in increasing order of finishing times. So in other words, at any stage, we're going to choose the earliest finishing interval that's disjoint from all the previously chosen ones. In other words, the local evaluation criterion is the finish time of I. So does one of these strategies yield a correct greedy algorithm? So if you want to try this as an exercise before I show the answer, then I'll give you a moment now to pause while I take a sip of coffee. Okay. So if you wanted a hint to try that, you just had no idea how to start that, and I'll give you another chance to pause here. Try to think if there are any inputs that would obviously cause you to return a non-optimal output for any of these strategies. So in other words, if I'm going to pick the earliest start time, can you make it bad for me to pick the earliest start time? So take a moment if you'd like to do that. Okay, so I'm going to assume by now you've paused and done that if you wanted to do that, and I'm going to try to reveal the solution. So for strategy number one, I'm going to prove here that this is incorrect. So what does it mean to prove that a greedy strategy is incorrect? Well, to do that, I only need to find one input for which the algorithm gives a non-optimal solution, or a broken, infeasible solution that violates constraints. Both of those would mean that the algorithm is wrong, because for an algorithm to be correct, it must solve every input and give an optimal and feasible solution for every input. So if there's any input for which it gives the wrong answer, where wrong means non-optimal or infeasible, then the whole algorithm is wrong. So all we have to do is find one input. It can be any kind of input we like. So we have considerable leeway to design an input that looks exactly like we want it to try to expose a bug in the program. Because finding any input, no matter how special it is, will demonstrate that causes the algorithm to misbehave, that is, will demonstrate that the algorithm is wrong. So for strategy one, where we're sorting and picking in terms of in order of increasing starting times, here's an input. Can we make it bad to pick the first starting interval? Yeah, make the first starting interval huge and make it prevent the selection of a bunch of other intervals. So here, for example, we have this input, which I'm going to render visually like this. So I'm going to draw a time, well, we're calling it the x-axis. Maybe I should have called it the time axis or something. Anyway, the x-axis or time axis is going to the right. And I'm going to draw multiple rows here because that's how I'm going to just represent intervals that I, of course, can't draw directly over top of one another so you can't tell what's going on. I have to draw them on different rows so you can see that they're distinct. So here's the interval from 0 to 10. Here's 1 to 3. Here's 5 to 7. And I'm going to draw all my diagrams for this lecture like this. Okay, so you can see if we pick the earliest starting one, we're not going to pick either of those two. So we picked one when we could have picked two. That's not optimal. This is a proof. Giving this example is a proof that an algorithm that sorts by starting times, that always picks the earliest starting interval, is incorrect. Okay, how about strategy number two? If we sort the intervals in increasing order of duration, can you make it bad for me to pick the shortest meeting? Well, it turns out you can. All you have to do is make the shortest meeting prevent the choice of a bunch of other meetings that are longer. So in this example, we have the meeting from 4 to 7 prevents me from scheduling 0 to 5 and 6 to 10. I could schedule 2 when I'm only going to schedule 1. That's bad. Now, strategy 3, where we sort in increasing order of finishing times, actually always yields the optimal solution. And I'm going to prove that. So first, I'm going to show you the code, because this is just to drive home the idea that this stuff is really, really easy to code up, and relatively speaking, hard to prove correctness for. So here's the actual optimal solution for greedy interval selection. We sort A by increasing finish times, and then we're going to start constructing our partial solution x. So we're going to choose the first element because it has the earliest finishing time. And then I'm going to remember what the index of the last interval that we actually kept in our partial solution was out of a. We took a of 1, so prev is going to be 1. And then for all the remaining intervals in the input, we're going to decide, do we take it or not? And we're always just going to look for the interval that has the smallest finishing time that doesn't overlap any previous intervals. So we're looking for an I, the smallest I, because smallest I means smallest finishing time, because they're sorted that way, such that A of i's start time is greater than or equal to the previously taken interval's finish time. So we have to wait, of course, until the previously taken interval ends. And then, because of our sort order, this start time is going to be, sorry, I'm saying something confusing. So we always need to wait until the previously chosen interval finishes, right? And then out of the intervals that start after that finishes, we want the earliest one. So we're just going to take the first one that we see that has A of I dot start greater than or equal to A of previous dot finish. We're going to append it to our X subset. Now, when I say subset, really this is implemented as an array, just an array, so constant time access. If you wonder how I'm doing constant time append, I can actually just allocate this as an array of size n at the beginning. So appending really just means writing to the next slot, the next free slot in that array. And at the end, I can return this array that's bigger than necessary and just also return the amount of the size that I actually used in it, the size of my subset, like k or something. So I haven't written that stuff here, but we can understand I'm not using some fancy data structure. I'm just using an array, and if need be, I can overallocate it so I don't need to deal with expandable arrays. Or I can assume I have access to an expandable array that gives me amortized constant time access, and then I'd have to be a little bit careful about my analysis because I have an amortized term, not a worst case term in there. So I just have to think a little carefully. Okay, but if I just assume I'm using a basic array, right, this isn't going to be very expensive. And then I've chosen interval I, so I set prev to I, because this is now the last interval that I've chosen. I just continue this process until I'm done. So for example, on our input that we saw before, these are some of our inputs. I've just labeled them here in order by increasing finishing times. A of 1, A of 2, A of 3. I'm going to take the earliest finishing times on first. So I'll take these two, which is optimal in this example. I'll reject that one. And then in this example, we saw that stumped the second strategy. Here's my labeling and increasing order of finishing times. And my algorithm will take A1. It can't take A2 because A2 overlaps this. You can see A2.s is not greater than Aprev.finish. Aprev.finish is 5. A2.s is 4. So it won't take this one. Instead, it'll go to the next iteration of the loop, and it'll see A3.s, which is 6, is greater than or equal to Aprev.f, which is 5, and it'll take this one. So it solves those two examples that stumped our previous two strategies. Where is our local evaluation function in this code, by the way? We never actually check out of all the choices we could make which one has the smallest finish time. Well, it's just embedded in the sort, right? We're taking the first interval that we can that doesn't intersect any previous intervals. That's it. Okay, so what's the time complexity of this algorithm? Well, we sort, and then we do one pass, and I've argued that this should be constant time for this store, constant time for this append. Everything in here is constant, except for the loop, which does constant work per iteration. So basically, it's theta n plus theta n log n for the sort. It's just theta n log n. Now, how do we prove that this is correct? In other words, how can we show that the returned solution x is both feasible and optimal? The feasibility is not too hard. Because we always choose an interval that starts after all of the other chosen intervals end. Right? How do we know that? Well, we can only append something to x if it starts after the previous interval ends. And the previous interval, of course, has a finishing time that's greater than all the previously chosen intervals, right? So this starts after all the previous intervals end. So we're always choosing something, we're always choosing an interval that doesn't intersect any of the previous intervals. If you want to choose that, prove that formally, then you do that with a loop invariant. You say, well, base case, when I enter the loop, I've only chosen one interval. So there are no overlaps. There's no overlapping in my x set of things I've chosen, or array of things I've chosen. So I assume now for my loop invariant, at the beginning of the loop, my invariant holds. I assume that everything in my x array, all of those intervals are pairwise disjoint. And I prove at the end of my iteration, whether I've added something or not, I prove at the end of my iteration that that loop invariant still holds. That will prove that at all times in the loop, and indeed once I exit the loop and I have fixed the array of intervals that I'm going to output, that array of intervals that I'm going to output contains pairwise disjoint intervals. That will prove feasibility. How about optimality? Well, that is harder. And unfortunately, there's no way to get away from doing a rigorous proof in order to prove optimality here. What is it this time? Maybe a glass shelf break? Oh no, that's better. Well, back to work. So let's do some greedy correctness proving. And I want to outline first at a high level how greedy correctness proofs are usually structured, and then give, of course, the concrete example. So a greedy solution x is correct. That's what we want to prove. And correct just means feasible and optimal. We typically show feasibility directly along the lines of what I just showed you, and optimality by contradiction, usually. In other words, we sort of suppose that the solution O, some solution O exists that is better than our greedy solution X. And then we want to show that that leads to a contradiction because, in that case, we've contradicted the existence of O, the existence of a better solution. Well, if we contradict the existence of a better solution, that means our solution must be the best, or at least must be tied with other possibly slightly different but equal in value solutions. And there are two broad strategies for deriving this kind of contradiction. In fact, it isn't always a contradiction. We'll see examples where it isn't. But there are two broad strategies. Certainly, contradiction is one way of doing it. There are two broad strategies for proving greedy algorithms, and they are greedy stays ahead arguments, where we show that every choice that we made in the greedy algorithm is at least as good as some corresponding choice in the optimal algorithm. So we sort of imagine that we look at the choices made by the greedy algorithm and the optimal algorithm in some order. And we don't necessarily know what order the optimal algorithm made choices in or how it works. We're imagining there's some optimal algorithm that does better than us. And we have no idea how it works. So we aren't assuming anything about how that algorithm works, but we know how our greedy algorithm works. And so we somehow order the choices that are made by our greedy algorithm and this optimal algorithm that we suppose exists. And we inductively prove that at all stages in our algorithm, if we reorder the choices made by the optimal algorithm in some way so that we can map them to the choices made by our greedy algorithm to define some correspondence between the choices made in our greedy algorithm and the choices made in our optimal algorithm, then we can show that every choice in X is at least as good as its corresponding choice in the optimal algorithm. And if all of our choices are just as good, the final result should be just as good. The second approach, and we're going to see an example of that in this lecture, the second approach that we're going to see an example of in the next lecture, and that might be helpful for your assignment, for example, is called an exchange argument. So an exchange argument involves, again, assuming that there's some optimal algorithm that we don't know that exists that can produce an optimal solution O that's possibly better than our solution. And then, if we want to come up with a contradiction, we show that this optimal solution can be improved by replacing some choice that it makes with maybe some choice that we made in the greedy algorithm, or just some other choice. As long as you can find a way of showing that some choice made in this supposedly optimal algorithm turns out to be non-optimal, then we can prove that that solution O is not really optimal, which is a contradiction. That contradicts the existence of this algorithm that produces this better solution O. Okay, so let's see the concrete proof for this problem. And this is actually going to be a greedy stays ahead argument, not an exchange argument. So we're going to give an inductive proof, where we prove that the sequence of choices made by greedy are, at each of those choices is at least as good as a corresponding choice made by the optimal solution. So the sequence of choices made by greedy, we're going to write that as I1, I2, all the way up to IK. And our partial solution, our feasible solution at the end, our greedy solution X, is going to be written as AI1, AI2, all the way up to AIK. And you might be wondering why I have double subscripts. Well, it's not A1 up to AK. That's the input. That would be a prefix of the input. We don't want just a prefix of the input. It chooses a subsequence. So AI1, AI2. The I1, I2 is adding a second layer of indirection. You can think of it as this is how you write a subsequence, right? So I1 is less than I2 is less than I3 is less than ... is less than IK. So this is an ordered subsequence of the input. Okay. And note, by the way, these intervals are sorted, and so this ordered subsequence is also sorted. Now let O be any optimal solution. O we're also going to write as an ordered subsequence of the input. But crucially, we are not assuming that the optimal algorithm uses the same sort order. Okay, we're writing down the choices made by the optimal solution in this sorted order. Whatever the choices it made, in whatever order it made them, we're imagining that we reorder those choices, because the choices are just intervals. We're imagining that we reorder those intervals according to increasing finishing times. But we're not assuming that the optimal algorithm actually makes the choices in that order. We're just writing them in this order so that we can form a correspondence, a one-to-one mapping between the choices of our made by our greedy algorithm and the choices made by the optimal algorithm. So we're creating here a correspondence between AI1 and AJ1. We're creating a correspondence between the intervals chosen by greedy, sorted by their finishing time, and the intervals chosen by optimal, sorted by their finishing time. So we're merely imagining reordering the intervals so that we can easily compare their finishing times to the intervals that were chosen by greedy, which of course were chosen in this order. So that ordering is just going to help us compare finishing times. So what we're going to prove as our key lemma in our greedy stays ahead argument is the following. We're going to prove that the finishing time of IM, like finishing time IM, is less than or equal to finishing time JM. Remember what this IM and JM are. The I sub something sequence represents the choices made by the greedy algorithm. And the J sub something choices represent choices made by the optimal algorithm that we've supposed existed. So we're saying for all m, for all m choices made by each of these two algorithms, the ith choice made by greedy has its finishing time less than or equal to the finishing time of the mth choice made by greedy in this ordering has finishing time less than or equal to the mth choice made by optimal in this reordered in this way. Yeah. Okay, so greedy's mth interval has finishing time less than or equal to optimal's mth interval. When I talk about their mth interval, it's just the mth interval in this ordering, sorting by finishing time, not the mth choice that optimal made in the order that it made its choices. Okay, so here's the proof. So we're proving by induction. So we have a base case where m equals 1. And indeed, we do have fi sub 1 less than or equal to fj sub 1, because fi sub 1 is the interval that the greedy algorithm chooses first, and it chooses the very first interval in its sort order, which is the one with the earliest finishing time. So there can't possibly be any other interval with a smaller finishing time. So this holds trivially. Okay, now we're going to prove the inductive step. So our inductive assumption is just the claim for m minus 1, and we're going to prove it for m. So by induction, we have f of I sub m minus 1 is less than or equal to f of j sub m minus 1. In other words, the m minus 1th interval, greedy's m minus 1th interval has finishing time less than or equal to optimal's m minus 1th interval in this order. Okay, so now consider AIM, in other words, the greedy's mth interval, and AJM, optimal's mth interval in this order. Okay, so what does this look like visually? Well, you have a sequence of choices made by greedy. You have a sequence of choices made by optimal. Consider now, okay, we know from the inductive hypothesis that greedy's m minus 1th choice, greedy's m minus 1th interval finishes at the same time or before optimal's m minus 1th interval, and we want to prove the same thing for m. So consider AJM, the mth choice for optimal, and AIM, the mth choice for greedy. Well, if you look at AJM, yeah, it starts, of course, since this is a feasible solution, after AJM minus 1 finishes. These have to be disjoint in order for this to be a feasible solution, and you better believe the optimal solution is feasible. So we have SJM is greater than or equal to FJM minus 1. And of course, by the inductive hypothesis, we have FJM minus 1 is greater than or equal to FIM minus 1. So we have the start time of this interval is greater than or equal to the finish time of this interval chosen by greedy. So what that means is greedy could actually pick this interval. Now, if we consider, of course, the interval AIM chosen by greedy, it's going to be chosen such that it has the smallest finishing time of any interval that starts after FIM minus 1. But we just argued that AJM starts after FIM minus 1. So this is one possible interval that greedy could choose. And greedy is going to choose the interval with the smallest finishing time that it can choose in this step. So whatever it chooses is going to have finishing time less than or equal to AJM's finishing time, because it can choose AJM's finishing time. Therefore, whatever it chooses will have finishing time FIM less than or equal to FJM. So that's the proof of this lemma, which will be useful. This is the crux of the greedy stays ahead argument. We've just proved, given our correspondence, where we considered whatever intervals were chosen by optimal in the same order that it made sense to consider the intervals chosen by greedy. Once we establish that correspondence by reordering the intervals chosen by optimal, we prove that for each choice made by greedy, that choice is just as good as the corresponding choice made by optimal intuitively. And it's not clear maybe that finish time of one being less than or equal to finish time of the other means that this is just as good, but the next part of the proof that uses this lemma should make it clear that this lemma enables us to prove that greedy obtains the optimal number of intervals. So let's use that lemma. So remember, the greedy solution x is ai1 up to aik, and the optimal solution O is aj1 up to ajl. And now we're going to complete the proof. So in order to obtain a contradiction, suppose that the optimal solution manages to select more intervals. In other words, L is greater than K. Well, from the lemma, we have that the finishing time of AK is less than or equal to the finishing time of JK. If L is greater than K, then the greedy algorithm selects AIK as its last block, last interval, and the optimal algorithm selects AJK, and then it selects something else. Okay, and AJK plus 1, the next block that the optimal algorithm chooses, of course by disjointness, so this is a feasible optimal solution, AJK plus 1 has to start after AJK finishes. So the start time, SJK plus 1, has to be greater than or equal to this finish time, FJK. And we know from our lemma that FJK is greater than or equal to FIK. So the start time, SJK plus 1, is greater than or equal to FIK. Sorry, I didn't pop these boxes up at the right time. So this thing starts after this finishes, and this finishes after this finishes, or at the same time as this finishes. So this has to start after this finishes. Okay, well, wait a minute. If this starts after this finishes, and this is the last interval in this sorted order by finishing times, chosen by Greedy, well, wait a minute. Greedy can choose this and obtain a feasible solution. So Greedy would choose this. Well, if Greedy would choose this, we know the Greedy algorithm. It would choose this. And somehow Greedy didn't choose this. That tells us that this block can't exist. This is a contradiction. The only thing we've assumed at this point is that L is greater than K. So the fact that we arrived necessarily at a contradiction means that the only thing we assumed, L greater than K, must be false. So L must be less than or equal to K. And of course, that tells us that this solution can't be better than X, our greedy solution. So our greedy solution is optimal. Okay, so that is our greedy stays ahead proof. Now, we can also look at a different proof. This is kind of a slick ad hoc approach. So I told you that usually we prove that these algorithms are correct using one of two different broad strokes approaches: greedy stays ahead arguments and exchange arguments. There are also some slick ad hoc proofs that you can come up with for certain types of algorithms that end up being really elegant and short. You can't always come up with them, of course, and they're not general strategies that have a particular name, but it's nice to demonstrate some such examples. So we're going to see a second very short one-slide proof of the same algorithm, optimality proof. So let F be the finishing times of the intervals in the array X that we return. So this, X is the greedy solution. These are the finishing times. They're ordered by their finishing times, right? So these are the greedy intervals. Now, note that no interval in the input can finish strictly to the left of Fi1 because greedy chooses the earliest finishing interval as its first interval. So no interval in the input can finish to the left of this. And also note that no interval can start strictly to the right, or else greedy would be able to take that interval without intersecting any of the previous intervals, so it would take that interval. So no interval starts strictly to the right. So all of the intervals in the input finish between here and finish after here, here or later, and start here or earlier. Okay, and no interval is contained strictly between these 2 points, between the finish I1 and the finish I2, because if an interval started in here and finished like somewhere in the middle, then greedy would have taken that instead of AI2. If it started before this point, it would intersect AI1, so it wouldn't be taken. But no interval can be in the input strictly between these points, or else greedy would have taken it instead of AI2. So in addition to the intervals in X, only the following types of intervals are possible. We can have an interval that overlaps Fi1 and this won't be chosen by greedy, so we don't get any contradiction. So yeah, this interval contains fi1. We could have an interval here that contains fi2. And we could have an interval that contains both fi1 and fi2. But we can't have any intervals strictly between this point and this point that don't contain either of fi1 or fi2, because they would be chosen, that interval would be chosen by greedy. And here we've said these are the intervals chosen by greedy. So we know in the input there are no intervals that lie strictly between fi1 and fi2. So if we restrict our attention to the intervals that are in the input, there are the intervals in X, and then there are these other intervals that contain finishing times. So this argument I just made for this space between AI1 and AI2, this applies for the space between AI2 and AI3, and AI3 and AI4, all the way to the end. So what this means is you don't have any intervals to the left, you don't have any intervals strictly in between these 2 points, and you don't have any intervals strictly between AI2 and AI3, and so on. And you don't have any intervals strictly between the finishing times of AIK-1 and AIK, and you don't have any intervals that start strictly to the right of this. So you just have the intervals in X, and then you have intervals that contain individual finish times or intervals that contain multiple finishing times. What this means is every interval in the input, apart from X, contains those in X contains a finishing time in F. Well, of course, the intervals in X also contain finishing times in F if we define them to contain their endpoints. So every single interval in the input contains some finishing time of an interval that was chosen by greedy. Moreover, no 2 intervals in O can contain the same finishing time. If 2 intervals that are chosen by an optimal solution contain the same finishing time, that means they overlap at that point, containing that finishing time. So you can't have 2 intervals that contain the same finishing time. So what this means is there must be as many finishing times as there are intervals in O, because 2 intervals can't contain the same finishing time, so each interval in O has to contain its own finishing time. We've said every interval has to contain a finishing time, so every interval in O has to have its own finishing time in F that it contains. So there can only be as many intervals in O as there are finishing times in F, and there are only as many finishing times in F as there are intervals chosen by the greedy algorithm. So that proves there are only as many intervals in O as there are intervals in the greedy solution. So that proves that there cannot be a better solution O. So that's kind of a slick proof. It's a little bit tricky, but yeah, hopefully that was interesting. Okay, so the next problem we're going to look at is called interval coloring. Well, you know what they say, 2 shelves, 2 breaks. Let's go for 10x speed so it doesn't look like I struggled for 30 seconds. Ah, nice and easy. Don't crack the glass. Wow, nice. Back to work. So interval coloring is a little bit like the interval selection problem, except whereas we tried to select as many intervals as possible to include in the output, here we're not selecting a number of intervals to include in the output. Every interval is going to be selected. The difference is we're going to give each interval a color rather than selecting which intervals appear in the output. So every interval will get a color. And the rule for feasibility is that if 2 intervals overlap in time, they should not have the same color. So you're allowed to overlap intervals, but you must color them differently. And roughly speaking, you could think of each color as a meeting room. So you're allowed to schedule multiple meetings at the same time as long as you have them in different meeting rooms. So what we want to find is a C coloring, that is, a mapping from the set of intervals to the colors 1 through C, they're just numbers, that assigns each interval a color so that no two intervals receive the same color if they're overlapping. They have to be disjoint if they receive the same color. So we want to output a C coloring that uses, for the optimality part of things, the minimum number of colors. So feasibility means don't color overlapping intervals with the same color. Optimality says use the smallest number of colors in total to color all of the intervals. So for example, we could just pick a different color for every single interval, and this would be a feasible solution, but it clearly is not optimal. So a couple of other examples, we can use here, we can't color these two the same way because they overlap, right? So this is not feasible. In this example, it's okay for these two to be colored the same way because they're disjoint. So this is okay. It uses 6 colors. We managed to reduce the number of colors by 1 by coloring 2 adjacent intervals the same color. And of course, we can actually color all of these intervals with 2 colors. And it turns out this is optimal, but how do we know that this is optimal? Could we do this with a single color? No, because clearly there's a point here where 2 intervals intersect. And if there exists a point where 2 intervals intersect, you gotta have a different color for each of those 2. So what kind of greedy strategy could we use to solve the interval coloring problem? Well, as usual, we're going to consider the intervals one at a time. And at a given point in time, meaning at any stage in the algorithm as we're making our various choices, suppose we've colored the first I intervals. So we've made our first I choices. What are our choices going to be? Well, for each of those first I intervals, we will have chosen a color. And suppose we've used D colors so far. Well, we have to color the I plus 1th interval. We're going to color it with any permissible color. What's a permissible color? It's a color that we can assign to the I plus 1th interval without overlapping any other intervals that have the same color. So if we want to color the I plus 1th interval with color C, it better not overlap any other intervals with color C. Okay? Now, if it can't be colored using any of the existing D colors, so we'll try to color it with some of the existing colors. We have D colors. If we can use any of those D colors, meaning if there's any color such that this I plus 1th interval doesn't overlap another interval with that color, we'll use that one. If we can't use any of those existing D colors, we have no choice but to introduce a new color, and so D is going to be increased by 1. And the question is, in what order should we consider the intervals? And of course, the order that we consider them in will encode our local evaluation function for selecting the interval. Okay. So we're going to color the I plus 1th interval with any permissible color, and the order that we consider these intervals in is going to matter. So let's see if we just color them using the basic input order. So here in the rows, I've drawn the intervals in the order that they're given in the input, A1 up to A10. So the first interval in the input was this one that goes from 0 to 3. The second interval in the input was this one that goes from 8 to 11. The third was this one that goes from 14 to 20. The fourth was this one that goes from 3 to 9, and so on. So if we consider the intervals in this order, and in each step we just color the interval using the first color that's available, what does it look like? Well, A1 here is going to get colored with the first color. So there are no colors at first. So we'll increment D from 0 to 1, creating a color. I'm going to draw color number 1 as this nice blue. And the second interval here we're going to color with the first color that we can apply to it, the first permissible color out of the existing ones. Or if there's no permissible color, we'll introduce a new color. So, well, this doesn't overlap any of the previous intervals that we've colored, so we can use the first color. And that happens to be true for the third interval here as well, too. Now interval 4 overlaps an interval with color 1, so we're going to need to increase d by 1, creating a new color. We'll make that color red. And interval 5 doesn't overlap. It does overlap an interval with color 1, but it doesn't overlap an interval with color 2, so we can reuse color number 2. Interval 6 overlaps an interval with color 1. It overlaps an interval with color 2, so we introduce a new color, 3. And interval 7 overlaps an interval with color 1. It doesn't overlap an interval with color 2, so we'll reuse 2. Interval 8 overlaps an interval with color 1, with color 2, and with color 3, so we'll increase d, creating a new color 4. Interval 9 overlaps color 1, 2, 3, but not 4, so we can give it 4, reusing 4. And finally, interval 10 overlaps 1, 2, but does not overlap 3, so we give it color number 3. So we've colored all of these intervals using 4 colors. But can we do better? Well, what if we sort these intervals by increasing start time? Then they look like this. And we can run the exact same algorithm, but now, of course, the interval that we're going to greedily assign the next permissible color to, the first permissible color to, is going to be determined by this sort order now, instead of the arbitrary input order. So you can think, what's our heuristic function deciding? It's deciding what's the next interval we are going to color using the first permissible color for that interval. Okay, so our heuristic evaluation function that we've embedded in our sort order is the first interval we're going to color at any given point in time is the one that has the smallest start time that we, of course, haven't already colored. Okay, so let's color A1. It's going to use the first color, and then A2 is going to overlap color 1, so we have to create a new color. A3 overlaps colors 1 and 2, so we got to create a third. A4 doesn't overlap color 1. So actually, by the time A4 starts, A1 has already finished, so this color is no longer used, so it can reuse number 1. And then, by the time A5 starts, A3 has finished. The A5 start time is greater than A3's finish time, greater or equal to A3's finish time. So we can reuse this color, color number 3. A6 here is now greater than equal to, well, it overlaps colors 1 and 3, but it's greater than equal to color 2 here. So we can reuse color number 2. A7 is greater than or equal, its start time is greater than or equal to the finish time of color 4, so we can reuse blue. A8, it collides with blue, but then color number 2, the red, we can reuse. And A9, it overlaps color 1, it overlaps color 2, so we have to use color 3, which is yellow. But now A10 doesn't overlap blue, so we can reuse that. And we managed now to color all of these intervals using only 3 colors. Is this optimal? What do you guys think? So I'm going to assume that if you wanted to answer, you've answered by now. We have to use at least 3 because there's a point in time here where all 3 of these intervals overlap simultaneously. And if all 3 intervals overlap simultaneously, clearly we need at least 3 colors. So this is optimal. So here's the algorithm for doing this. We sort the intervals by increasing starting time, and just for notation's sake, I'm going to pass around the start times and finish times in that sorted order. So I'm going to call return interval coloring SF, where these are the start and finish times of the intervals as they are sorted by increasing start time. In other words, these start times will be increasing, and these will be the corresponding finishing times to each of these start times. So f of I will be the corresponding finish time for s of I. Okay? So here's the algorithm. We have d, color, finish. These are our sort of key variables that we're going to work with and reused. So d is the number of colors we've used so far, lowercase d. Color of I is going to be the color that we've assigned to interval I. So we'll start off by assigning color 1 to interval 1. And then finish of I is going to be, finish of C for a color. So the index here, the index of this color array is the interval number. So for each, this has an entry for each interval. So there are n of these entries. Finish of C, the index here is a color. So there are only going to be as many entries of this array as there are colors. And initially, to avoid having to use expandable arrays here or something, we can overallocate. We can make finish have n elements, and maybe we just won't use all of those slots. We're only going to use the slots up to d. Okay, so finish of C is going to be the finish time of the last interval that received color C. So every time we color an interval with a particular color, so if we color it with color C, we're going to store in finish of C the finish time of that interval. So it just so happens that the one here and the one here are the same, but this is because color 1 is being assigned to interval 1. These ones represent different things. This represents a color, this represents an interval. Okay, so now we give interval 1 color number 1, and then for each of the remaining intervals, we're either going to reuse a color, and we'll check if we can reuse any of the colors 1 to d that already exist, or if we weren't able to reuse any of those, then we'll create a new color. So for each interval ai, we search for an appropriate color c to use by iterating over all the colors from 1 to d. And what's the condition for us being able to reuse a color? We're going to check if we can reuse any of these colors. For us to reuse a color, let's think about what makes that possible. Consider the interval ai that we're trying to color here. It has start time si and finish time fi. And we want to try to color it with color C. When are we allowed to color it with color C? Well, if the start time of our interval is greater than or equal to the finish time of the last interval that received that color, so that color, the last time it was used, was before we started. That means we can reuse that color C without breaking feasibility, because we don't overlap with that last interval that used this color. So if finish time for that color is less than or equal to our start time, we reuse the color. We set the color for our interval to C, and we set the finish time for that color to our finish time. Because now we can't reuse that color until our interval, which uses that color, finishes. So we're going to be the new interval that is the last one to use that color. And we set this flag that says we did manage to reuse a color, and we break out of this for loop. So now we jump to this if statement. And if we didn't manage to reuse anything in trying out all the colors C in this for loop, then we create a new color by incrementing D. We set our color to D, and we set the finish time for color D to our finish time. Finally, once we break out of this loop, we've assigned a color to every interval using, of course, the greedy algorithm that we just described. And so we return the number of colors that we actually used, D. Okay, here's some things for your notes. This is stuff I've said. Okay, so let's see an example of running that algorithm with the variables that I introduced in the previous algorithm. So this is running the pseudocode. Previously we saw running the algorithmic idea. Let's see running the pseudocode. So here's the initial state where we've done the sort, and now we're going to start trying to assign colors. Before the loop, we just assign color 1 to A1, and then in the loop, our D is 1. We're going to if this, of course, is our finish. Sorry, this is all the initial stuff we did. We set the color, we set D to 1, and we set the finish time of color 1 to the end of this interval. Now we're going to try to assign colors to the rest. So for each of these remaining intervals, we're going to loop over all the possible colors. And that's from 1 up to D, and D is 1. So that's only the first color. So we're going to check, is finish 1 less than or equal to the start of the second interval? No. Okay, so we can't reuse it. So we have to create a new color. So increment D, create a new color, assign it to this interval, and set the finish time of color 2 to this interval. Okay, now we're going to check for A3 if we can reuse a color. So first of all, is the finish time of color 1 before the start? No, we can't use that. Is the finish time of color 2 before the start? No, we can't use that. So we have to create a new color, and we assign it, and we set the finish time for color 3 to the finish time of this interval. Now, for interval number 4, we're going to check, can we reuse any of the colors 1 to 3? Well, is the finish time for color 1 less than or equal to start time? Yes. So we can reuse color 1. And the finish of color 1 now changes to the finish time of this interval. Okay? And we can repeat this process for all of the remaining intervals. And I won't walk through all of the steps. I mean, you can see these animations yourself. You don't need me to talk through them. You can verify this. This just continues until we've assigned a color to every interval. Okay, so let's reason about the correctness of this algorithm. So rather than showing a greedy stays ahead argument or an exchange argument, I'm going to give you another slick proof, because there is actually a nice ad hoc proof for this algorithm, and this is quite a well-known problem and algorithm with a really nice proof. So let's give you the nice proof. So let capital D be the number of colors that end up being used. In other words, the return value of the algorithm. And let F sub D be a special interval. This is going to be the first interval that is assigned the last color D. So the last color that's created, this is the first interval to get that color. So essentially, this is the interval that necessitated the creation of that color. And we should be able to argue that this color, when this color was created, we really needed to create it. So we're going to highlight this special interval FD and talk about it. Okay? And let LC be the last interval that has color C and starts before FD ends. Okay? So I don't care about the intervals that started after FD. I'm going to talk about the intervals that started before FD ends. Okay? I don't care about the ones that start after FD ends. All the ones that start before FD ends. So basically just ignore everything that happens in the execution after FD finishes. Just think about what happens before FD finishes. And select the last interval that has color C that starts before FD finishes for each color C. We're going to prove that FD actually overlaps every single one of those intervals for every color. In other words, we're going to establish a time when there were D intervals that all intersected, so we really need D colors, and that will establish that we have an optimal return value D. So if D is 1, the proof is immediate. It's trivial, right? If D is 1, there is one interval, the FD, that got the last color, and there's one interval that needs one color, so okay. But what if D is greater than or equal to 2? Well, okay, we're going to let FD and LC be defined as we just described. We're to prove that FD overlaps every interval LC. So I've drawn all the LCs here. So the first, this is the last interval to receive color 1 that starts before the end of FD. This is the last interval to get color 2 before the end of FD. The last interval to get 3, 4, 5, and so on, all the way up to D minus 1. Now let's argue that L1 must exist and must overlap FD. So first of all, it must exist because otherwise Greedy would just use color 1 for FD, right? If there is no LC, what does that mean? LC is the last interval that has color, so L1 is the last interval that has color 1 and starts before FD ends. If there's no such L1, then there's no interval that has color 1 that starts before FD ends. So that means there's in this entire, everything from the end of FD to the beginning of the execution, the beginning of time, there's no interval with color 1. Well, then, of course, the greedy algorithm will just use color 1 for D. That's a contradiction, because we're saying there were D colors used, and this is the first interval to get D. D was created here. When this interval received color D, D was created. So we know the greedy algorithm would just assign this first color in that case, unless this L1 already existed. And we can make, and the finish time of L1 has to be after FD starts for the same reason, because if the finish time of L1 was before FD starts, then again, there would be no reason not to reuse color 1 here, because color 1 would not overlap interval D, and the greedy algorithm would pick color 1 here. But there is an interval color D. This is the first one, so that means the finish of L1 has to intersect with this, so that the greedy algorithm will say, I can't use number 1, I have to create a new color D. And the same reasoning applies to all of the other L's, all the way up to LD minus 1. So we know that L1 finishes during FD, L2 has to exist and has to finish during FD, and so on, all the way up to LD minus 1, which must exist and must finish during FD, or possibly at the end of FD. So what this means is FD overlaps D minus 1 other intervals, and in fact, every single one of these intervals contains the start time of fd, and so does fd. So there are d intervals that all contain the start time of fd. So that is d intervals that all overlap at a single point in time, which implies there must be at least d colors. But d is our return value. So d is, if we prove feasibility, which I think was fairly straightforward, I leave that to you as an exercise, then clearly d is enough colors, and d is also the minimum number of colors we can have. So d is exactly the optimal answer. Okay, so we must use d colors. Okay, so that's the optimality proof. I didn't do the feasibility proof. I sort of talked through it intuitively when I described how the algorithm works. So you could do the feasibility proof as an example. Prove that no two intervals that overlap receive the same color. Okay, now if you want to talk about the time complexity briefly, this sort is going to take n log n time. And then restructuring this a into an s and an f. This is really just it's not. This isn't something that you would necessarily have to really execute, right? I could have just encoded a in a way that let me sort it and also let me access its start and end times efficiently. So these two, lines 3 and 4, don't really represent steps that need to exist in the algorithm itself. But even if they were just naively copying all the contents of A into S and F, it would still only take time that's linear in N, which would be dominated by the sort cost. So it doesn't really matter for the complexity. So we have an n log n time plus a call to greedy interval coloring. Greedy interval coloring is going to do order n iterations, and in each of those order n iterations is going to do order d, or up to order d iterations, because it might break early as soon as it finds a color that works. And of course you're going to do constant time inside this innermost loop, and this is constant time, and this is constant time. So we're just going to have a total runtime that's order n log n plus nd. Okay, so well, what's this runtime? I mean, if d is small, suppose d is like a small constant, like we managed to use like 7 colors, then this is just order n log n. But if d is really big, well, how big could d be? We might need a separate color for every single interval. So this might be n times n, which is n squared. So the runtime actually depends on the number of colors. So the most accurate complexity statement that we can give is theta n log n plus nd, where d is the number of colors used. Okay, now if we wanted to come up with a more efficient version of this algorithm, we might want to stop for a second and think about the inefficiencies that exist in this algorithm to see, could we make it faster with, for example, some clever usage of data structures? And my eye certainly jumps straight to these two loops. Do I really need to try every color? Because this is a search problem. I'm really searching for the first C that makes this true, right? Because as soon as I find a C that makes this statement true, I'm going to break. Well, what's this statement? Its finish of C is less than or equal to S of I. So I'm looking for, well, if I could find the C value that has the smallest finish time, then I'd have the best chance of satisfying this expression, right? If finish of C is less than or equal to Si for the C that has the smallest finish C, okay, great. If the smallest finish C doesn't satisfy this expression, then every other finish C will also not satisfy this expression. Like if the smallest finish C is greater than Si, all the bigger finish C's will also be greater than Si. So really I just need to find the smallest finish C. Okay, so that's basically what is being said here. Really we're looking for some finish C that's earlier than the start time of I. So we're really doing a linear search. And maybe we could do something more efficient. So one thing we could do is we could use a priority queue to keep track of the earliest finish time for a color, to find what's the color that's sort of expiring or coming up for reuse the earliest. And hopefully we can use that one. Okay, then we only need to look at the minimum element. And we could use a data structure that can implement a priority queue abstract data, because a priority queue is an abstract data type. And there are lots of data structures you could use to implement it. But there are certainly data structures that can implement a priority queue very fast. So looking at the minimum element can be done in constant time with a particular choice of data structure, like a binary heap. Looking at the minimum element can be done in constant time. And dequeuing the minimum element can be done in logarithmic time. And enqueuing a new element, or pushing a new element into the priority queue can be done in logarithmic time. So we could do much better than a linear search, potentially. So what if we came up with a heap-based algorithm? So imagine that we have now a heap that's going to store our finish times. So instead of an array of finishing times, one for each color, we have a heap. Okay, so in the first iteration, we're going to check the heap minimum. If it's empty, then we need a new color. So we're going to create a new color and put it in the heap, put its finish time in the heap. And the heap is going to be ordered by finish time, these finish times for these colors. So when we come to the next interval we want to color, we're going to check, is its start time greater than or equal to the minimum finish time in the heap? Well, minimum finish time in the heap is 3. Well, 3 is after this, so this is not greater than the minimum finish time, so we can't reuse a color. So we have to create a new color, and we create it and we push it into the heap with the finish time 7. We're going to do the same thing for the third interval. Now for the fourth interval, when it comes time to check if we can reuse, we're going to take the start time, which is 3, and we're going to compare it with the minimum on the heap, which is 3. Ah yes, we see we can reuse this minimum element on the heap. So we reuse the color blue, and now that we've reused it, so how do we reuse it? We delete min, to go back a couple steps. We see, yes, we can reuse it because we checked the heap minimum, and our start time was greater than or equal to the heap minimum, so we can reuse it. So we delete min, so we reserve the color by deleting it from the heap. And then we see what's our new finish time. It's 9. So we push that color back into the heap now. We insert it into the heap with our finish time of 9. And so who knows how the heap is organized internally, but the 9 is not the minimum element. The minimum element here is this yellow color, which has finish time 5. So when it comes time to assign a color to A5, we're going to compare with the heap minimum. Our start time of 6 is greater than the heap minimum, so we'll reuse this color with finish time 5, the yellow, by deleting min, reusing it for our interval, and then reinserting it back into the heap with a new finish time, and so on. So we're going to continue this process, and so on and so forth. Okay, so here's the pseudocode. The pre-processing is all the same. And for the greedy interval coloring code, we do the same, creation of the first color and assignment of it to the first interval. But now we create a minimum priority queue, which is going to be implemented as a min heap. And we're going to insert pairs into that min heap. So the pairs are going to be ordered by their finish times, which are the first element. But we're going to include the color. Sorry, this shouldn't be color. No, this is right. So this is the color. We're gonna insert the pair finishing time of interval 1 and color of interval 1 into the heap. So when we pop out the minimum element of the heap, we receive the finishing time. That's also what we compare against when we look at the top element of the heap, and we receive the color. So we know what color that finishing time corresponded to. So that's why we put pairs in. We can't forget what color the finishing time corresponded to. Okay, so for each element here, I'll talk about complexities in a second. For each element, we look at the minimum element of the heap, which gives us the finishing time for that color and the color. If the finishing time for that color is less than or equal to our start time, we can reuse it. So we delete that top element from the heap, and we use that color, the color C. Otherwise, if we couldn't reuse that color because the finishing time of that color was after we start, then we create a new color and we color ourselves with that new color. And in each case, whether we reuse a color or create a new color, if we reused a color, we deleted the color from the heap, so we need to put it back on the heap. If we create a new color, we need to put that new color on the heap. So in each case, we insert our finishing time, because of course we colored ourselves with that color, with whatever our color is, color I, and we push our color onto the heap as well. Okay, so what's the time complexity of this? Well, inserting takes log s time, where s is the size, but right now the size is 0 when we first do this. This is actually constant time, not that it really matters. This won't be a dominating cost. Then we have our for loop with order n iterations, and in each iteration we look at the minimum of the heap, which minimum of the priority queue, which for a binary heap implementation takes O of 1 time. And then our check here takes constant time. Our delete min takes order log d, where of course the size of the priority is log size of the priority queue, and the size of the priority queue will be however many colors it contains, which is at most d. So this is going to be order log d time to delete the min. And this is for a binary heap representation. So if you remember your binary heaps, deleting them in means taking the last element and taking a hole at the bottom and bubbling until you reach the root. I hope I didn't misspeak on that. At any rate, it's not important for this course. If you don't remember how binary heaps work, you can look that up. Yeah, arguably I should have done that. Okay, and then there's the insert here, which also takes order log d time. So what we have here is a loop up to n where we do order log d work in it. So it's n log d time for this whole loop. It's n log n time for the sort here, and then it's constant time outside of that loop. So we have order n log n plus n log d time. And actually, sorry, I have this backwards. D is less than or equal to n. This should be backwards. I'll fix that on slides. D is less than or equal to n because the most colors we could have is n. D is less than or equal to n, so that means n log d is at most n log n. So this whole expression from the min rule ends up turning into theta n log n. So without the clever use of a priority queue, a heap-based implementation, we ended up with n log n plus nd runtime, which could be n squared in the worst case. Now we have something that manages to solve interval coloring in only theta n log n time. Okay, so with that, I'll end the lecture. Thanks for listening, and I'll see you guys next time for more greedy algorithms. Bye.